Welcome back to the Electronic Lab Notebook playlist on the scimax channel. I'm going to take a break from the surrogate model work that we had in the last couple of videos and return to the design of experiments. And I covered this in a few previous videos, and we did those manually. We used PyDOE3 to set up the design and then set up the outputs and then do the regression. And all of that was a lot of work and a lot of repetitious code that you would have to repeat over and over. And that isn't how you want to do something like a design of experiments. You really want a much more streamlined approach that is simple with a few lines of code. So I've had in mind a sklearn-like package for design of experiments, where we follow the API that the design is like a model, and then you fit it with the X inputs and the Y outputs, and then you have all of the capabilities of sklearn like it. And so today I'm going to show you how that looks in its present form. This is kind of alpha code in PyCSE, but it looks pretty reasonable and pretty light on the amount of code that's required. Okay, so you can find these links are the previous work that we did, first in just doing a regression, second doing some analysis, and here we have an example of a surface response class that I wrote, and it is in the GitHub Bleeding Edge PyCSE library. Okay, so this is sort of the first piece. We're looking at the SDL-Light instrument. We have three variables that we can use as inputs, the red, the green, and the blue setting. And we're going to measure three outputs, and I call these R0, G0, and B0. And we want to build a design that is in the range of 25 to 75 for settings in each one. So this is the concise implementation that we use to specify the design that we want. Now, under the hood, we currently I only support box banking designs. In a future version of this, we might try to expand that to include other kinds of factorial designs or other things that are available in PyDOE3. But for now, we just support box banking, and that's what it is. All right, so I'm going to create an instance of the surface response, and then I just call sr.design, and this is going to give me now directly a list of experiments that need to be run that are saved in this variable called input. And this is just a data frame, and now it's up to you to figure out how do I make a corresponding data frame that has R0, G0, and B0 that are measurements for each one of these. I've already taken the liberty to shuffle this, so these are to be run in the order presented, and the index here is indication of the original order. But we want to run these now in the order that goes here. Okay, so to do these, again, this is old code that you've seen many times. We set up a function that runs this observed sensor data, and then our measurement is going to return three numbers, the red, the green, and the blue channels from the measurement. And I use hash cache because they take, again, 7 seconds or so to run. And for the sake of this, I don't want to make you sit around for a minute. Okay, to run these, we just iterate over the rows, and you can see here I started this post 2 days ago, so it's taken a while to actually write that surface response class and fine-tune it and test it and add things to it. And let's see, in here I think we can get rid of this index now, so I'm going to get rid of that. Basically what we're doing is accumulating an output. So for each row in the input, we make a measurement, accumulate that, and then I call set output with that data. And that makes a new data frame that is the outputs. So these are the red, the green, and the blue intensities that are measured for each one of these experiments in the same order as the input. Now, if you weren't doing this all in code, if it wasn't all Cloud Lab, you might have to create an Excel sheet, and you might enter manually some measurements, and then you might use pandas to read that Excel sheet to generate this data frame, but I'll save that for another day maybe. Okay, now the analysis, this is where we use the kind of sklearn-like, and it's sklearn-like. I decided here that since we already have set the input and the output as variables, I don't use the x comma y here. This is going to run the fit and do the analysis for us. We're going to print the score. This is a benefit we get from sklearn, and I have a parity function here that will give us a parity plot. And so you can see we have a very, very good R squared that's visible here in this parity plot. These are the true values versus the predicted values. So we have a very high quality model here with the second order surface response. I didn't mention that. That was the default that you use the second order. Okay, so that looks pretty good. We can do a little bit of analysis of variance. I'm not a very sophisticated statistician when it comes to this, but we have created some summary here that tells us how many data points we have, the score. These are the mean absolute errors and the RMSEs for each of the channels. So you can see they're kind of small-ish, certainly on the scale of errors. These are quite small. And I have here output for the parameters that are specified. Now this one is a little bit tricky because we have 3 outputs and there are parameters for each output. So the parameters of the model here will be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 rows by 3 columns. And so I'm doing a column-wise analysis here. So these are the parameters for the red channel, and confidence intervals kind of lower and upper, and the standard error associated with it, and then whether it's significant. So 1 means it's significant, and if it was 0, that would mean that there is a confidence interval that contains 0. Now, I feel like I'm missing a column here that maybe ought to be the parameter value. But maybe this is good enough. We're never going to use these parameter values directly, but you might want to look at some of these later and see. This one you can see is actually just barely relevant. The lower confidence interval, these are 95% confidence intervals, almost includes 0 for it. We have for the green output, we have an example here of a parameter that is not that significant. It includes 0, for example, and so you could leave it out. That's not too surprising from what we know. The red LED is quite far in nanometer space from G, and so this tells you the red setting doesn't affect G at all, and that here's another one that isn't necessarily significant. And then for the blue output, you see, again, red doesn't really impact the blue. You have a confidence interval that includes 0, and the rest of them seem, reasonably relevant. Now, in other design of experiment packages I've seen, they would calculate p-values and do f-tests and tell you if it's significant based on p being less than, say, 0.05. And here I'm taking a more heuristic view that if the confidence interval includes 0, then there's a reasonable chance that it is 0 and that it's not relevant. That's true for this linear model. Certainly there's room for more significant analysis in here than I'm doing. Okay, we can use our design of experiments now to make predictions. This is one of the reasons why using sklearn is nice, is that once we define the SR object, we can make a prediction. And here I use a data frame. Since we trained with a data frame, you get a warning if you don't use a data frame. And so we can use this to get predictions and uncertainties on the predictions if we say return underscore std equals true. And that's a feature of the underlying linear regression model that I used in the surface response class. So I think this is pretty useful. Let's try one like maybe outside and see what it says. Here we try it at 0, and you see some negative values that aren't even physical, but you see higher uncertainties here. That is an indication that something is not reliable in the prediction. But it's also a little bit overconfident here, and this could reflect. Let's try 100. Could reflect, limitations of the measurement. So even if we go outside to 100 or 200, then you see these uncertainties start to grow and are much bigger than the uncertainty, the MAEs that we've seen, and that ought to be an indication that this is not a reliable measurement. Lastly, we can set up an objective function. So if you wanted to, find where the model would give an output of, say, 10,000, 10,000, 10,000, then we can set up an objective function here that we're going to find a minimize on this, and then we can run this and see that we get an output. And so this suggests setting it to 43, 59, 35 should give us a reading of 10,000, 10,000, 10,000. And down here, if I check that solution, you see that it is quite close to it. And if you've been watching any of these videos before, you know that we can't actually get 10,000, 10,000, 10,000 from this device. The outputs are discretized, and there are gaps in the output space. Nevertheless, this is pretty close, and I think it is pretty convenient for it. So let me make myself a list of things here now that I've talked through this. And I think we probably want actual parameter values in the summary report. It doesn't seem like it would be not like the most important thing that we need, because we'll never use these for anything other than looking at them. But I suppose sometime in the future, somebody might actually take this text and use it instead of using the actual digital versions. Let's see, was there another thing? I think that was the main thing that I thought we ought to have in there. I think it might be nice if these were rounded and not quite such a high decimal count. Yeah, I think that's going to be all that I work on to change this. All right, so that is the brief kind of introduction into an sklearn-like DOE package. This one, again, this is just version 1 of this. It only supports the Box-Banken design. I have to look and see whether the other possible designs like factorial and whatnot have a similar enough signature that it's easy to substitute them in as another argument to the surface response. So I think this is a lot cleaner code. Certainly it does a lot more for a lot less. That's because it's all buried in the surface response.py code. You can find that on GitHub in the pycsc.sklearn directory if you want to see how it is. And otherwise, stay tuned for future developments of this package and how we can use it in your electronic lab notebooks. All right, thanks for coming.